Hello, my shimmering stars. Today, I, Shora Grover, welcome you all to this amazing platform of PW English. Students, I welcome you all to your Nexus Batch. And today, we are going to start with your chapter S block elements. Till now, students, we have done the hydrogen chapter. That means we have covered the very first element of the periodic table. Now it's turn to move on to the block part. That means S block, P block, D block, and F block, right? In your class 11th standard, basically we have S block and P block. We have only two groups. Then in your class 12th, we have other groups of P block elements 15 to 18 and the DNF block, right? So let's proceed with the S block elements today. Today is going to be the very first lecture of this particular chapter. And let me tell you, it basically contains two groups. That is group number 1, group number 2. And we are going to do that one by one. So today I'm going to start with group number 1 in detail. Then tomorrow we'll be doing group number 2. And after that we'll be doing the compounds related to both the groups with more and more questions, right? So students, let's proceed this session with a beautiful smile. So this is going to be lecture number 1 for the S block elements chapter. And let's discuss about the sequence for our today's class. So initially we are going to start with the introduction part, that what are the S block elements and why are the elements placed under S block category. The next part is we'll be understanding group number 1 in detail, the properties, physical and the chemical ones, right? So let's proceed with the very first topic, that is introduction to the S block elements. So students, if I'll talk about the introduction to S block elements, you very well have seen the periodic table. I guess you all have that at your home as well, because everyone has that. A chemistry student will always have a periodic table with him or her, right? So basically, if I'll talk about the periodic table, students, you have seen the complete periodic table. But yes, let me highlight what are the group number 1 and group number 2 and where they are placed under the periodic table. So in periodic table, if you'll take a look, S block elements are placed at the left hand side position of the periodic table. This is the right hand side position, this is the left hand side position. So S block elements are placed over here. Moreover, it contains two groups, group number 1, group number 2 respectively. Group number 1 holds hydrogen, lithium, sodium, potassium, rubidium, cesium and francium. We have understood in our previous sessions that why hydrogen is placed above the alkali metals. Now, what are alkali metals, ma'am? Group number 1 are referred to as alkali metals. So, hydrogen is placed above here, though it has a controversy that it exhibits both the properties of group number 1 and 17, but we have understood that in detail, right? So, basically, lithium, sodium, potassium, rubidium, cesium, francium, these all are alkali metals and are referred to as group number 1 elements. If I'll talk about group number 2 elements, students, they are beryllium, magnesium, calcium, strontium, barium and radium, right? These are your group number 2 elements, which are also referred to as alkaline earth metals. Though there is one exception, I will be letting you know that which of the following is not an alkaline earth metal, but yes, it is placed under group number 2. We'll be coming to that part, right? So now students, I'm going to write all the elements over here in detail. We'll be writing about the electronic configuration, the atomic number, all the introductory part over here, right? Okay. See, if I talk about S block elements, so it majorly contains two groups. Group number 1 and your group number 2, right? So this is what is an S block elements comprised of. Now talking about group number 1 in detail, what are the elements over here? We have hydrogen that we have already studied. Other than this, we have lithium, we have sodium, we have potassium, we have rubidium, we have cesium, we have francium. Let me tell you students, francium is a radioactive element. So I'm going to put a star over here. Okay. Now moving on to the group number 2 elements, we have what? We have beryllium, we have magnesium, we have calcium, we have strontium, we have barium, and then we have radium. And again, radium is a radioactive element, so I have put a star over here. Now coming back to their atomic numbers. So there is one trick to remember the atomic numbers, that is 2, 8, 8, 18, 18, 32. Basically, this trick is your magic number. This trick is your magic number that, by the way, you can learn the atomic numbers. So you should know the initial element's atomic number, and with the help of this trick you can determine the other element's atomic number, because it is a huge periodic table. So it's better to do that in a trick format, right? So let's start with hydrogen. We know atomic number is 1. Now just add these number. Add 1 plus 2 comes out to be, ma'am, 3. Now 3 plus 8 comes out to be what, ma'am? 11. 11 plus 8 comes out to be what, ma'am? 19. 19 plus 18 comes out to be what, ma'am? 37. 37 plus 18 comes out to be what, ma'am? 55. And 55 plus 32 comes out to be what, ma'am? 87. So these are the atomic numbers of these elements of the group number 1. Talking about group number 2, atomic number, we should know the initial element's atomic number. Beryllium holds atomic number 4th. If you don't know what is the atomic number, remember lithium, with regard to lithium, it is at the right hand side position, so you'll add one number. 3 plus 1 is 4. Now just determine the other values. You have to start from 8 now instead of 2. So add these number. 4 plus 8 is 12. 12 plus 8 is 20. 20 plus 18 is 38. 38 plus 18 is what, ma'am? 56. 56 plus 32 is what, ma'am? 88. So this is one way, or the another way is, if you know the group number 1 element's atomic number, just add 1 into it, you will get group number 2 atomic numbers, such as 3 plus 1 4, 11 plus 1 is 12, 19 20, 37 38, 55 56, 87 88. Now the next part, students, that you should know about them, that group number 1 elements are basically referred to as alkali metals. Alkali metals. And if I'll talk about the group number 2 elements, so group number 2 elements are referred to as alkaline earth metals. Alkaline earth metals, students. And let me tell you, there is an exception. Beryllium is not an alkaline earth metal. Why? Because it exhibits a characteristic of amphoteric nature. It is not alkaline in nature. That's why, yes, it is exhibiting the properties similar to group number 2, but it is not an alkaline earth metal. It is a group number 2 element only, due to the similarity in the properties. Now, why they are placed under group number 1 and 2 respectively? Due to their, properties, similarity in properties, right? That's why they are placed under the same group. Now talking about why they are placed under the S block elements, we'll come to the electronic configuration. I will explain you that part. Talking about the alkali metals, why they are alkali metals? Due to their alkali behavior. Because they exhibit alkali behavior, that's why they are alkali metals, right? Now moving on to students, now we'll be studying today about group number 1 only. When I'll be coming to group number 2, I'll be discussing about that in detail, right? So about hydrogen, students, we have already covered, so I'm not going to discuss hydrogen again and again. I'll be only discussing from lithium towards francium. Clear, everyone? So I'm going to start with the very first part, that basically what happens. These are referred to as alkali metals because they form hydroxides on reaction with water, and basically they are alkaline in nature, right? Now when I talk about the abundance part, students, so sodium and potassium are abundant in nature, while if I'll talk about lithium, rubidium and cesium, they have very much low abundance. And if I'll talk about sodium and potassium, students, in detail, their importance, so they are basically used in nerve impulse functioning. So if you have read in your biology part, you may very well know that Na positive and K positive have a role in the nerve impulse part, right? So moving on to the next, we very well know that francium is highly radioactive. I've already put a star. If you want to learn the half-life of the isotope, where we have an atomic mass of 223 of francium, and that case half-life time basically is 21 minutes only. So this is just the introductory part of the S block elements, and especially of group number 1 in detail. Starting with, students, your electronic configuration to S block elements. Let's everyone write down all the elements again. So it's hydrogen you have already done. So I'm starting with lithium, sodium, potassium, rubidium, cesium, francium. So basically the atomic number is 3. Then we have to add 8. So it's 11. Then again 8, 19. Then add 18 into it. You will get 37. Then add 18. You will get 55. Then add 32. So you will get 85. Right? Sorry, you will get 87. You're adding 32 into it, 87. So now if we'll talk about the electronic configuration, students, of lithium, you should know it is 1s2, 2s1, right? Similar in the way of sodium, if you'll go, it is 1s2, 2s2, 2p6, 3s1. So if I'll talk about the general electronic configuration, what are you going to observe? That the outermost electronic configuration is going to be ns1. What it is going to be, ma'am? general electronic configuration for group number 1 is going to be NS1, where N represents your period number or the shell number, I would say. Yes, everyone? Period number or the shell number. Now, when I'm discussing about the electronic configuration only, what is the observation you have seen? That they contains one electron in the outermost shell, and all of these, when they lose one electron, they form cations. So they have a capacity to form cations, right everyone? For example, sodium when loses one electron will form Na positive, right? Similarly, lithium when will lose one electron will form Li positive. Potassium when it will lose will become K positive, right everyone? So basically they have a cation formation capacity. Also students, they are electropositive in nature. They are electropositive in nature. Clear everyone? So this was about the electronic configuration and the general electronic configuration. Moving on to the properties part, I'm going to start with the atomic radius. Let me first explain what is a radius. What is an atomic radius? For example, if I'm talking about lithium, let's discuss. Lithium has an atomic number 3, so it's 1s2, 2s1. How I will draw the structure? This is your center, nucleus, then your first shell, then your second shell, students. Right, everyone? So if I have to write lithium 1s2, 2s1. So the 1 refers to first shell. First shell contains 2 electrons. Sorry, first shell will contain maximum of 2 electrons. Second shell contain only 1 electron. Right, everyone? Only 1 electron. So this is the structure. Now what is an atomic radii? Atomic radii is distance from the center towards the outermost electron. Let's draw this another one over here so that you can get an idea. Yeah. So the distance from the center to the outermost electron is basically your radius. Is your radius, students. Right, everyone? I don't know, students, whether is the structure being visible to you or not, but it's okay. Yeah, so no problem. Really sorry, students. I guess I was about to show you the structure, but it was not visible. No problem. I'll draw it again. I'll draw it on my own. So I was drawing the structure that I was drawing over here, such as I have drawn of lithium with atomic number 3. So I have drawn it like this. First shell, second shell. First shell contains 2 electrons, second shell contains 1 electron. So the distance from the center to the outermost shell electron basically is your atomic radii, right? Now when I'm talking about atomic radii and the trends, let's talk about that. So what do you observe from lithium, sodium, potassium, rubidium, cesium, francium? What is happening here? Basically it is 2s1, the outermost configuration. It is 3s1, 4s1, 5s1, 6s1, 7s1. Yes, everyone? So basically that means what is happening from top to bottom, we are observing that number of shells are increasing. This is an increasing sign, right? So from top to bottom, if number of shells are increasing, distance from the center to the outermost electron will also increase. That means atomic radii, students, atomic radii is going to increase. Okay, let's draw if you want to. Here it is 3. I'm taking just the 2 examples. You'll get an idea with that as well only. So it's 11 basically. Now see. If I'll write the complete electronic configuration, 1s2, 2s1. If I'll write about this, it is 1s2, 2s2, 2p6, 3s1. So let's draw both the structures. In lithium, we have first shell and the second shell. In sodium, we have first shell, second shell, and the third shell, 3s1. In potassium, if you want to draw, it is going to be like this now. First shell, second shell, third shell, fourth shell. Similarly, in rubidium, it is fifth shell, sixth shell, seventh shell. So if number of shells are increasing, distance from the center to the outermost electron is also increasing, students. That means atomic radii from top to bottom is going to increase. Also remember what happens along a period. When you go along a period from left to the right direction, nuclear charge increases and hence the size decreases. Okay, so basically this is the trend along a period. Let's talk about it. With increase in atomic number, the atom becomes larger. Okay, the monovalent ion, that's M positive, are smaller than the parent ion. Now what do you refer to this line? I'm going to explain you this line now. See, basically if I compare, let us say I'm going to compare lithium and Li positive. Let's compare lithium and Li positive. So if I'm going to draw the structure for lithium, what is going to be lithium configuration? 1s2, 2s1. Now what is, when is positive sign created? When we lose one electron, we gain a positive charge. So it is going to be 1s2 when one electron is being lost, because 2s will be 0. No? So if I'll draw both the structures, in lithium I have first shell and second shell, where I have one electron in the outermost shell, and the distance from the center to the outermost is atomic radii. If I'll draw lithium positive, it will have only one shell. Why? Because here it has lost one electron, so 2s0 becomes the state. There is no electron in the second shell. So if you'll automatically observe, if we are creating a cation, it will have a lower atomic radii than the parent ion. Why? Because if it is losing one electron, it is losing one shell automatically, because in the outermost shell it has only one electron. So that means size is going to decrease for that case. So atomic radii, if I'll talk about ion and atom will have more atomic radii than ion. So this is given over here. The monovalent ion M positive were smaller than the parent atom, sorry. The atomic and the ionic radii of alkali metal increases on moving down the group, that we have seen, as they increase in size while going from lithium to cesium. Clear everyone? Simple part, easy portion. Okay. Let's ma'am move on to the next segment. I would say that please students kindly write down all of these so that we can move on to the next property of it now. Shall we, students? Shall we start with the next property? Very interesting property now. Very interesting. That is going to be ionization enthalpy. Now ma'am, what is ionization enthalpy? Let's first understand and then I'm going to read it, right? So basically students, ionization enthalpy is the energy, not the energy, right? Minimum energy. Minimum energy required to remove an electron from the outermost shell of isolated gaseous atom What is an ionization enthalpy? It is basically the minimum amount of energy that is required to remove one electron from the outermost shell. That means the last shell, right? Now that is ionization enthalpy. Now let's consider the case. Let me tell you first of all the factors on which it depends. It depends upon size. Always remember, ionization enthalpy, which I am referring to as IE, it is inversely proportional to size. It is inversely proportional to size. So if I am writing lithium, sodium, potassium, rubidium, cesium, francium, I am saying from top to bottom, number of shells are increasing. So size is increasing, right? If size is increasing, ionization energy is decreasing, because they are inversely proportional to one another. Also, one more thing, students, here I have written atomic radii will increase. So this is going to be the order which will have the highest size, francium, right? As it is radioactive, so if we are not considering that in question, cesium will have the highest, right? Coming back over here, if I'll talk about ionization energy, it is going to decrease. So what is the order of ionization energy is going to be that lithium will have highest, then sodium, then potassium, then rubidium, then cesium, then francium. Now let me explain you why is it inversely proportional to size. Now see, we have to remove one electron from the outermost shell, right? In lithium, we have only two shells, while in cesium or francium, if I'll talk about, I have 6 and 7 shells, right? So for example, if someone is standing so close to me, right? and and someone is pulling them apart, let us say someone is pulling them apart, so I won't let that person go who is standing close to me, because I have some bonding with that person, I have force of attraction. Now if someone is already standing at a far more distance from me and someone is pulling them from outside, so they can easily go, no, because the force of attraction is not that much strong as it is when it is close to me, right? This what happens over here. In the case of lithium, the electron, outermost shell electron, is close to the nucleus, so it is exhibiting the force of attraction. Nucleus is positive, electron is negative. It is having some force of attraction. So you have to give a lot of energy to break, that force of attraction and liberate the electron outwards. And if I'll talk about a case where there is a, greater atomic size, so a larger radius, so electron is present at a far more distance. So if you'll give less energy also, we can easily go out. Why? Because force of attraction is less in comparison to the one where the distance is less, right everyone? So that means in the smaller ones, you have to give a lot of energy to remove that electron from the outermost shell, while in the case of the atoms which are larger in size. So as ionization energy is inversely proportional to size, and hence we get this order. Now, there are two important more factors that you should know. But before that, let's read this. Ionization enthalpy of the alkali metals are considerably low and decreases down the group from lithium to cesium. Right? It is decreasing. This is because the effect of increasing size outweighs the increasing nuclear charge, and outermost electron is very well screened from the nuclear charge. So this thing I've already explained with the help of example. Now, other things that you should know, let's discuss about which will have the highest ionization energy or enthalpy, group number 1 or group number 2. Group number 1 or group number 2. Now see students, in group number 1, the general configuration is NS1. Here it is NS2. You should know that duplet or the octet condition basically is the stable one. Here we have only one electron in the outermost shell. Here we have completely filled configuration, NS2 configuration. Now when you are removing an electron from a stable configuration, you have to give a lot of energy to remove that electron. That means in this case a lot of energy will be given to remove that electron, because it is already stable. NS2 configuration is duplet condition, which is already stable. So when you are affecting or changing any impact, or you have to remove one electron from a stable configuration, you are going to finish its stability, right? Now when you are going to affect the stability, basically you have to give a lot of energy. That means in this case ionization enthalpy of group number 2 is going to be more of with regard to group number 1. Now this is first ionization energy, so I'm writing 1 over here. This is first ionization energy. Now if I'll talk about the second ionization energy, second ionization energy of group number 1 and second ionization energy of group number 2, what do you feel now? Now what is second ionization energy? Second ionization energy is something when you're removing another electron. First is something when you're removing one electron. Second is something that you're removing one more electron from that state. Okay, that means total of 2 electrons are being lost. Now see what happens. If I'll talk about this state, firstly you removed one electron, right? Now this becomes stable. Why? Let's take a case of sodium. Sodium and magnesium. We're going to take two cases. Sodium is group number 1 and magnesium is group number 2. Magnesium is atomic number 12. Its atomic number is 11. So configuration is 1s2, 2s2, 2p6, 3s1. Its configuration is 1s2, 2s2, 2p6, 3s2. Right everyone? Now see, when we removed one electron, this was first ionization energy. When we removed one electron, it was first. So the state becomes what? 1s2, 2s2, 2p6. This is which case? When we removed one electron, it became Na positive. When we removed one electron, it became which state? 1s2, 2s2, 2p6, 3s1. It became 3s1 on liberating one electron, on loss of one electron. Now you have to remove one more electron. Just write for one electron on removal of one electron. Right? Don't write the charges. Now we are removing one more electron. See, here it has 2p6. 1, 2, 3, 4, 5, 6. Here it has 3s1. Now this is a stable configuration. If you have to remove one more electron, you are now affecting the stability of this one. Over there, you don't have to give this much energy. But over here, when you will remove one electron, you are affecting the stability. There it will gain stability after removing one more electron. It will become Mg plus 2. But here, if you are doing that, you are affecting the stability. That means ionization energy 2 value of group number 1 is more in comparison to group number 2. So this thing, students, you should know. Very simple yet interesting one. Yet interesting one. Right? Clear, everyone? Yes. Shall I move on to the next one? I would request each and everyone to please kindly write down each and every thing that I have written over here, so that now I can start with the next property of yours. Next property. Shall we? Okay. Now, students, comes the next property, that is hydration enthalpy. Hydration words refers to when we are talking about what? Water. Very simple thing. Okay. So when I'm saying that alkali metals in their forms of ions, right, when they are dissolved into water, so they are dissolved in the form of ionic form. Let us say, if I'm talking about sodium, sodium in its ionic form is Na positive, no? So when it is doing an interaction with water molecules, when water is taken as a solvent, and there is a bonding between Na positive and the O negative part of water, so that is basically at that spot of time, the energy released is hydration enthalpy. So what is hydration and enthalpy? The energy released when the alkali metals react with the water molecules. So the ions of alkali metals react with the ions of water molecules. It at that spot of time, the bond created and the energy released at that spot of time is hydration enthalpy. Right. So the hydration enthalpy of alkali metal ions decreases with increase in ionic size. This is going to be the trend for the hydration enthalpy. Why? Remember that hydration enthalpy is inversely proportional to the cationic size. And as we know, from top to bottom, size is going to increase. So hydration enthalpy will what happen? It will decrease. Very simple part. So if I'm writing the ions over here, if you'll be talking about the ions, Li positive, Na positive, Ka positive, Rb positive, Cs positive, what happens? From top to bottom, we know size increases because number of shell is increasing. So hydration enthalpy. So hydration enthalpy, students, will decrease. It will decrease. Simple, easy. Now see, lithium positive has maximum degree of hydration because it is decreasing. So lithium positive will have maximum hydration enthalpy, and for this reason lithium salts are mostly hydrated. They are mostly hydrated. Right, clear everyone? Just write down about hydration enthalpy. Now we will be proceeding towards the next property of yours. If this is done, students, let's proceed further to the next property now. So there are some more physical properties, but before that, I want to discuss with you the oxidation states. So just cut, this is not chemical properties I'm discussing, but yes, I am discussing about oxidation state now. See, students, oxidation state, I am talking about both group number 1 and group number 2 that you should know. For group number 1, students, the oxidation state is plus 1. And for group number 2, the oxidation state, students, is plus 2. It is plus 2. Okay. What is an oxidation state? If you don't know, oxidation state basically is the formal charge on any element. The formal charge present on any element. Yeah. So the formal charge on any element is referred to the oxidation state, or the other name is also oxidation number. It is also oxidation number, the formal charge on any element. So group number 1 has plus 1 oxidation state and group number 2 basically has plus 2 oxidation state. Clear everyone? Now students, if I'll move on to the next property of yours, we have discussed a lot of properties. Let's talk about the reducing power. Let's discuss. I don't know why is this magic happening. One or the other words just get missed everywhere. Yeah. See, the D goes over there with the white color. I don't know how it is happening. So, if I'll talk about the reducing power students, yes, let me tell you, group number 1 has the stronger reducing power than group number 2. But yes, the reason I want you all to think the reason and write in the comment section. This is one homework, because I feel that you should try something by your own. Think, use your mind, try to write the reason in the homework of reducing power, though I will be letting you know in the next session also, because we are going to compare both of the stuff of group number 1 and group number 2. So yes, first of all, students, write down oxidation state, the reducing power. Now we have done a lot of the properties over here, students. We'll be now moving on to the density and the melting point and the boiling point. Let's start with, first of all, the melting point and the boiling point. I don't know why is this magic happening today. Yeah, okay. So about melting point and boiling point, basically melting point and boiling point is going to decrease, down the group. If I'll talk about, it is going to decrease. Decrease down the group. If I'll talk about the melting point and the boiling point, it is going to decrease down the group. And if I'll discuss about basically the density part, let's start with now that density. Yeah, let's discuss about. Yeah, let's just discuss about density. Now we very well know, students, density is what? Density is mass by volume. That means density is directly proportional to mass. So if I'll ask in group number 1 from top to bottom, we know that ma'am, mass is increasing. That means size is increasing. So density will also increase. Simple part, because it is directly proportional to mass. That is going to be what? It is going to be lithium, sodium, potassium, rubidium, cesium. I don't know why it is happening. Okay. So basically what is happening, density will increase. But there is an exception, students, that you should know. There is an exception. This order is incorrect at some point of view. Why this order is first of all incorrect, ma'am? What is the reason behind this? See, between sodium and potassium, what is going to happen? As I'm saying, density is going to increase. So order should be like this. But over here, order should be like this, but it is wrong. It is wrong. Potassium basically will have a lesser one than sodium. Sodium will have more. Why? Because in the case of sodium and potassium, what happens? D orbital penetration effect takes place. And due to that here, we will say that volume factor will takes place. Here, due to the penetration of D orbital, we say that volume is increasing, and volume is inversely proportional to density, so density will decrease. Other than that, mass will dominate, but over here in the case of sodium and potassium, which factor will dominate? The volume factor will dominate, and hence the density is going to decrease. Same will happen in the case of group number 2. So we will be discussing about group number 2 in the next class. But yes, here today we'll be only discussing about group number 1. So everyone, please kindly write about this so that we can now proceed with the next part. Okay. Let's proceed with the next part, next property. Now comes the physical properties with regard to the flame coloration concept. Let's discuss about that. All the alkali metals are silvery white, soft and light metals. Because of the larger size, these elements have low density, which increases, down the group from lithium to cesium. Right, basically, students, now density I've already told you it is going to increase, but yes, there is an exception which I've already told you. Now, however, potassium is lighter than sodium. So this is the thing I already told you. There is an exception of density which I've already discussed. The density is going to increase down the group, and this is the exception part which I have explained you. The next thing, melting and boiling point of the alkali metals are low, indicating weak metallic bonding due to presence of only single valence electron in them. Now, what is a metallic bonding? The bonding between the kernels and electrons is metallic bonding, no? So, it is going to be weak in this case due to the presence of only one electron. Coming to the next part, the alkali metals and their salts impart characteristic color, okay, to an oxidizing flame. This is flame coloration concept. They are going to impart color, students, right? This is because the heat from the flame excites the outermost orbital electron to a higher energy. From a lower energy to a higher energy, one electron will excite, and when it comes back, it will impart some colors. So, when the excited electron comes back to the ground state, there is an emission of radiation in the visible region which imparts color, right? So, what are the colors that are being imparted? This you should know. Among alkali metals, if I'll talk about, lithium and cesium is generally asked. Lithium has basically the crimson red color, and cesium basically has a blue color. Cesium has blue color. Right. Now, other than this, students, if you want to learn, sodium will impart yellow color, potassium will impart violet color. Okay, lithium, sodium, potassium, rubidium. Rubidium will impart red color. So this is the colors if you want to learn. But yes, these two are really important. Lithium, crimson red, and cesium is blue. In group number 2, we have certain elements that don't impart any color. We'll talk about that in group number 2. So, but before that, I hope so. Now, these all properties are clear. This was about the general color that we talked about. Density, then melting and boiling point, then comes your the flame coloration part. Clear, everyone? Just write it down so that now we can start with the chemical properties with regard to your group number 1 elements. Yes, everyone. Okay. Now let's start with the chemical properties of group number 1, students. So first of all, I'm going to start the reactivity towards air. Okay. So the very first I'm going to start is reactivity towards air. Now see what happens, students. Basically, they react very fast in air, the very first thing, and they burn very fast in air. So we are going to give you some example. Then when they're going to burn, in air, they either are going to form, see, now they're going to form different kinds of oxides, monoxides, peroxides, and superoxides. So group number 1 can form all of these 3. Yes, students. Okay, let me tell you the reaction. See, when lithium basically reacts in the presence of air, that means with O2, it is going to form a monoxide. That is Li2O. Right? If I'll talk about the next one, lithium, then we have sodium. So now when sodium, students, reacts with O2, what it is going to form? It will form peroxide. That is Na2O2. When I'm talking about other elements, lithium, sodium, now come potassium, rubidium, and cesium. Now, potassium, rubidium, and cesium, that means I'm talking about here potassium, rubidium, and cesium. So I'm writing only M, okay? It can be potassium, rubidium, or cesium. When it is reacting with O2, it will form superoxide, that is MO2. Okay, so remember, lithium, when it's react, it is going to form monoxide in the presence of air. Sodium, when it is going to do, it is going to form peroxide, and potassium, rubidium, cesium will form superoxide. And one more thing, students, let me tell you, lithium is the one which basically can react with which basically can react with nitrogen and create nitride. Only lithium among the alkali metals. So it can also create nitride. Lithium, when reacts with nitrogen, can form Li3N, which is a nitride of lithium. Right, everyone? So this is the reactivity towards air that I have written. Now we'll be moving towards the reactivity with regard to water, everyone. So everyone just write it down. Now we're going to write the reactivity with regard to water. Done? Yes. Let me tell you, students, they are highly reactive. They are highly reactive with water, the very first part. And when they react, they form hydroxides. For example, metal basically refers to as your alkali metals over here. So when it reacts with water, it is going to form your hydroxide, liberating what? H2, liberating dihydrogen. Let's take some example. Lithium, when it reacts with water, it will form LiOH, liberating dihydrogen. Sodium, when it is going to react with water, it is going to form sodium hydroxide, liberating dihydrogen. Similarly, potassium, when it is going to react with water, it is going to form potassium hydroxide, liberating water. Clear, everyone? So you should know about them in detail as well. They are highly reactive students. Clear, everyone? Clear, 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 clear. Yes, everyone just write down, this is basically the reactivity with water. Now we're going to do with the halogens, we are going to do with other compounds, their reactivity. So now we're going to start towards towards, first of all, let's do with dihydrogen, then halogens and so on, right? So now reactivity towards dihydrogen. See, this we have already done. Dihydrogen is what? H2. Now let me tell you, this reaction will take place at 673 Kelvin, but there is an exception of lithium. In the case of lithium, it will take place as 1073 Kelvin. Other elements will do this reaction at 673 Kelvin, but lithium will do this at 1073 Kelvin only. It will react with dihydrogen at that case only. And when it is going to do that, it is going to form ionic hydrides. It is going to form ionic hydrides. So do you remember in hydrogen chapter when we discussed about hydrides part, I told you ionic hydrides, right? Clear? Remember, everyone? Ionic ones, yes. Okay, ma'am. So what is going to happen if I have a metal? It is going to react with H2. That means with dihydrogen, it is going to form my hydride. It is going to form my hydride. And let me tell you, lithium hydride is the stable one. Lithium hydride form is basically the stable one. Clear, everyone? So this is basically the reactivity with dihydrogen. I would request each and everyone to write down. Till then, I'll drink a glass of water, please. Okay. Now I'm going to talk about the reactivity with halogens. Reactivity towards halogens. See, students, when I'm talking about the reactivity towards halogens, for example, if I have metal and it is going to react with halogen, it will form MX. What it will form? MX. Simple part, easy part. And the one which is more stable is least reactive. Also remember, reactivity and stability are inversely proportional to each other. So this also you should know. Other than the students, now when it is going to react with mercury, let's talk about its reactivity with mercury. What it is going to form, students? Let's take an example of sodium, Na. Now when sodium reacts with mercury, that is Hg, will form sodium amalgam. What it will form, ma'am? Sodium amalgam. One more thing, students, here X can be fluorine, chlorine, bromine, iodine and so on. Right, everyone? And the last reaction over here that you should also know, that is reactivity with sulfur and phosphorus. So they can also react with sulfur and phosphorus and create certain compounds. For example, if it reacts, sodium reacts with sulfur, it is going to form what? Na2S. Okay, in the same way, it can react with phosphorus and create Na2P. Clear, everyone? So this is basically the reactivity with sulfur, the reactivity with phosphorus, the reactivity towards halogens, and the reactivity towards the dihydrogen part. Clear, everyone? Is it clear to each and every one of you? Now, students, this ends our chemical properties over here, and it also ends our chapter over here. Not chapter, today's portion over here. So there is two more properties that we'll be discussing about that in next part, that is going to be related to some of the reaction of organic chemistry in the chemical property of group number 1. Only two properties. And after that, students, we are going to do group number 2 in the next lecture. After group number 2 in third lecture, we are going to cover the compounds and the questions, right? Today I have not brought any question because I want you all to read from NCERT. The very first homework for today is to read this from NCERT. Because whensoever I'm talking about inorganic chemistry, I always say to you, you students that inorganic chemistry is something which is theoretical. Though here is a lot of things that we have understood today in our class, right? But what I feel is when you're going to read it, no, after understanding the chapter from mine, you are going to read it, you will get that concept in detail. It will retain in your mind. So it's better students revise this particular session today and read it from NCRT. And yes, be prepared for next lecture because we are going to do the topic, we are going to do the questions with regard to 1 and 2 together, and then to the next part, right everyone? So now students, I will be meeting you in the next lecture. Till then, keep smiling, keep learning. Thank you so much and take care of yourself. Thank you students.